Hello, everyone. Let's get started. So I'm Abhishek, also known by my security handle Inferno, and I'm going to talk about Clusterfuzz. So some bits about me. I live in California, USA, and I am one of the initial members of the Google Chrome security team, joined in 2010. Fuzzing is my passion, and especially fuzzing at scale. I can describe you the level of enjoyment I had when I got my first 100 virtual machines to fuzz upon. And that continues till today when we are fuzzing using 4,000 dedicated VMs. In the early days, I used to contribute a lot to WebKit, and I have found and wrote patches for at least 350 bugs. In my spare time, I have also reported security vulnerabilities to other browsers like Firefox and Safari. So here are some Chrome vulnerabilities, trends for both internally found and externally reported vulnerabilities. So back in the year 2009, as you can see here, when we had a new browser, a new security team, and not many external researchers looking at Chrome, we had less than 5 vulnerabilities a month to triage. And fast track to 2014, we have more than 60 bugs a month to triage. So that's a lot. To save us from all this manual triage, we created this fully automated fuzzing infrastructure living in the cloud that we coined as Clusterfuzz. And this mammoth infrastructure produces more than 100 million test cases a day and has found more than 1,600 security vulnerabilities. Let's dive into some details now. So the front end of Clusterfuzz is all on Google App Engine. So this includes the Clusterfuzz UI, the task management system, which uses the App Engine pull queues, the data store, which stores the crash metadata, like which crashes were found and stuff. The backend of Clusterfuzz is mostly virtual host on Google Compute Engine. So this includes our VMs on Windows and Linux. And a part of this infrastructure is also in the Google Chrome lab. So this includes our physical devices for Android, the Mac servers, and the physical Linux GPU boxes. So what does a bot do? It does one of these tasks highlighted here. The lowest priority task, or the basic task that every bot does, is fuzzing. So a fuzzing run generates like 1,000 test cases, which we feed to a target application like Chrome and monitor for crashes. Once a crash is found, we create a high priority minimize task to shrink down the repro to its smallest size without affecting its reproducibility. And once that is done, we create 4 parallel tasks, like one for getting better stack traces, one for knowing the test case impact, like which production branches are impacted, one for knowing when this test case regressed, and lastly, a recurring task which runs once per day to know when this test case got fixed. So what really led to the inception of Clusterfuzz are these 3 goals. The first one is full automation of crash detection, analysis, and management. And this is dependent on these 5 action items. The first one is, obviously, you need to have a good fuzzer. For people who don't know what fuzzing is basically a way to generate like an invalid or unexpected input to your target program. And it could be used for a number of purposes, not just security, like things like catching memory leaks and so on. In this case, one of the first things we want, which works across all of our fuzzers that we run on this infrastructure, is to have a common semantics, like which helps for easy pluggability. Things like which is the input directory to get the existing test cases from, to mutate. The second is which output directory should we put the first test cases in. How many files we have to process for a run. So things like that. And then we have these set of tags that we use in the test case name to guide the infrastructure. So things like a fuzz dash tag would indicate that this is the file to run on the infrastructure, because there can be like multiple resource dependencies as well in your output folder. Or things like if you want additional flags to be passed on, like when you're testing like an experimental feature, so those could be put in this flags file, and so on. Most of our fuzzers are written in the platform-independent like scripting languages, because it saves us from all this compile headaches and managing across these different platforms. So that was about fuzzers. So what sort of role does the infrastructure play? It takes away all the complexities of things like setting up builds with different sorts of memory debugging tools. It chooses the random metadata for a particular fuzzing run. So things like what sort of fake keyboard or mouse gestures to run on this test case, or what sort of memory debugging tool settings should I use, like what sort of red zone should I pick, or quarantine size, and so on. Some of the other things it does is it tries to find out the resource dependencies as well and bundle them in an archive along with the test case. Other things it does as well are making sure it's reproducible. And it does it by testing it on that same bot and also on the other bots, which are all similar configurations. And lastly, one of the most important thing it does is test case deduplication. So this is really important, because if we don't do it, we will have like thousands and thousands of crash stack, and which manually a person cannot triage. So these are the techniques that have really worked for us to generate unique test cases. The first one is we actually disable the inline frames completely. To give you an example, these kind of inline frames are usually optimized frames in header files that can be really common across different crash stacks. So things like, let's say, decrementing a ref count of an object, or like accessing an element at a particular index in a container class. So we disable those, and then we use these 3 parameters to decide the uniqueness. The first one is the crash type. So this we get from the tool itself we use, which I will talk about later. Crash state, which we get from the top 3 stack frames. The reason we ignore the line numbers is we are continuously testing these builds, and there could be code refactorings involved, so we don't account the line numbers. And lastly, the security flag, which is based on a couple of factors. So things like crash address, whether it's near null or non-null, or what is the crash type, and so on. So now you understood the basic structure. Now let's go about writing a fuzzer. So before writing a fuzzer, you need to understand what are the different types of fuzzers you can write. The first one, and what we call as a most basic one, is a generation type fuzzer. As its name says, it generates the test cases from scratch. So it is usually used to test like an isolated area. So things like the CSS parser, or let's say the editing APIs, those we have been really successful there. Or one of the external reporters who submitted a fuzzer to us found a lot of web audio bugs. So things like that. And here, since we are generating everything from scratch, we have to build up a lot of the initial state for testing. So to give you an example, let's say if you are fuzzing HTML parser, you cannot just like pick a set of like 3 tags and be done with it. You need to generate a lot of tags, build a lot of state, build different attributes and stuff. And we have seen with these kind of bugs, these kind of fuzzers, they generate a lot of bugs in the initial state. But let's say if your code is not changing much, those fuzzers fade with time. So then there comes the mutation-based fuzzers. The mutation-based fuzzers are actually based on an initial test corpus of files. So what we get help here is these existing test cases are actually written by like real developers and not just fuzzer writers like us. And they help to already test a part of the functionality of the code. So they build up the initial state we need. So these kind of fuzzers don't need to mutate the test case so much. They have to just mutate a little so that the test case remains valid and we test these states. And we have found them really useful for like file format, protocol fuzzing. and stuff. To give you an example, another area where it was really successful is the V8 JavaScript engine. So in there, we found that it's pretty easy to combine different like tests together if we normalize the different variables and function names and put like arbitrary function calls and change values. To give you an example here, this was a bug, actually a regression, which was really caught really quick by our fuzzers. It really just required flipping a few indexes, and the bug was actually in the function optimization code. Basically, what that means is when you run a function multiple times in JavaScript, it optimizes the code. So in this case, what happened was the bounce check was actually only done at the start and end and not in the middle. So this caused like a heap buffer overflow. So lastly is the evolutionary fuzzers, or what we call as intelligent fuzzers. So before we discuss that, let's first talk about code coverage. What does code coverage mean? So code coverage basically tests like how much parts of your code is covered, and that also gives us like how much like surface area we are testing in the code for security. The first metric is actually function level coverage. So if you don't have any code coverage at all, this is a really good thing to start with. But as you can see here, it only tells whether you just entered a function or not. And that's about it. And this gets really deceptive if you have, let's say, a function whose first line does like a parsing check of a certificate file, and that fails, and it just bails out of the function. So it isn't really testing the remaining part of the function, which is the core, like the core part which you want to fuzz. So what helps here is the block level and edge level coverage. For folks who don't know what basic blocks are, those are like smallest code entities which have a single entry and exit points. So in this code, as you can see, the blocks covered are B, C, and D. And then there is another set of coverage which is even more awesome than block level coverage, is the edge level coverage. And what it gives is the transition between these basic blocks. So things like, if in this case you want to check whether you are really covering both the null and non-null cases of the integer pointer, you need edge level coverage. So what code coverage are we using? We are using the coverage that is provided as part of the address sanitizer tool. It's like crazy, crazy fast. So you can forget like the traditional slowness of tools like, I'm pretty sure you guys would have used like gcov or lcov. And those are extremely slow for two reasons. The first one is they rely on counters instead of a plain Boolean. And the Boolean itself is really sufficient for us because that's what we want to know, right? Whether we reach that part of the code or not. So that is one. And other thing is that tool creates like thousands and thousands of tracking files. So the I/O overhead really slow down our VMs. So instead, the ASAN code coverage just generates like a single file per process, and it's very quick. So we have code coverage implemented for both Android and Linux, and the Clang support for both Mac and Windows is in progress. It should be probably done sometime in the next quarter or two. So now coming back, so evolutionary fuzzing is also called as feedback-driven fuzzing. And this feedback loop is usually the code coverage that I talked about before. It requires additional instrumentation, and it's just like just setting a runtime, like an environment variable, not much. But there is actually a little overhead involved. Like for edge level coverage, it could be like on average like 20%. But that is still very good because you don't have to use a separate build. You can use the same build which you use in your fuzzing. And also for this kind of fuzzers, you need all of your different bots to share this kind of intelligence. So they need to share, okay, which test cases they have tested so far, what sort of aggregate code coverage they have covered. So for making this task easier, we have implemented this API that we provide to every fuzzer. This helps to create like a coverage metadata file. And this helps the infrastructure to do automatic corpus distillation for you. So to give you an example, let's say you have a bunch of like 100 files, and initially you just started with not modifying these files at all. Like you were just running them, you were just running them in the application itself. So you can indicate via a flag that like if they are not contributing to any new code coverage, just delete them. And I want to retest with like a smaller or better corpus. So this allows for that. The other things are, let's say you modified, let's say, like a video file, and that helped to cover like new code areas. Do you want to add that back to corpus? So these are kind of the decisions we help using this API. And this slides talk about that in a little more detail. You can read about that later. By the way, if you have any questions on any of these slides, feel free to nag me anytime during the next 2 days. So I hope everybody's still awake. So having a fuzzer alone is not sufficient to find bugs. If you really want to find all the bugs, even the bugs that don't result in necessarily a crash, you need a really awesome memory debugging tool in your arsenal. And I think everybody or most of you might have actually used Valgrind, and I don't know, I at least gave up on it pretty quick. The reason being it's extremely slow for fuzzing, like at least on an average like 20x slowdown. And the test case minimization is next to impossible because that can need like up to like 100 or even thousands of iterations. So instead, we use all these memory debugging tools. These ones, and the ones that I will talk in the next slide and two, are developed in Google in-house by Costia's team. And these are all based on compile time instrumentation. So they are really fast. The first one is the address sanitizer tool. That is like the, what you say, like the father of all the sanitizers tools. It was the first one that came back like 4 years back and finds a whole bunch of security stuff like heap use after freeze, buffer overflows. And it's also much better than Valgrind because it helps to instrument the stack variables and global variables too, with a minimal slowdown, like less than 2x on CPU and less than 2x on memory too. The next tool we use is Thread Sanitizer. Thread Sanitizer tool is known to find data races. However, some of these data races can have security implications. So these include like data races on object vPointer, or cases of data races could be when you have a heap use after free crash, but the crash and free are on different threads. So it's more reliable with TSAN. In fact, when we get an unreliable repro from ASAN, we do try to run it with TSAN to see if it becomes reliable. Next in our list is this new shiny tool we got last year. This is called as Memory Sanitizer, and it helps to find all your uninitialized memory reads. So I don't know if you noticed in that vulnerability slide, there is a huge peak. That is because when we integrated the Memory Sanitizer tool, and it just found like hundreds of bugs. So this tool is really good. The only thing you have to be really careful about is the false positives. And those false positives come because if you're not instrumenting the system libraries right. So at least in Chromium, we don't have that problem because we support a dedicated JIP flag where you can build with that configuration. And MSAN is able to look inside all the memory initializers. And its speed is still pretty quick, like 3x CPU and memory 2x, so still pretty fast. The last tool I'm going to talk about is the undefined behavior sanitizer. This is like a work in progress integration that is going on. It claims to find several classes of bugs, like 19, but only a few are security relevant. So one of the really awesome ones, awesome class of bugs that it finds is the bad casts. So we have completely integrated the v-pointer functionality of this tool, and it has like almost negligible CPU and memory overhead. Lastly, I will probably just skip over these tools. These two tools are Windows specific and are based on dynamic binary translation. So they are a little slower than the compile time instrumentation tools, but still they gave us pretty good coverage at the time when we didn't have like ASAN on Windows. Now we have it. So these are some examples which you can read later. Okay, so next item in our list is scale. So scaling is really important for two reasons. One is we want to find out all the regressions as soon as possible. Like many of our regressions we catch in less than 24 hours. The reason is because of these thousands and thousands of bots. The other reason is, as you know, fuzzing is all about randomness. So the more bots you have, the more random test cases you can test out with. So it really helps to find new bugs too. We have the most scale on Linux because all of these memory debugging tools, they start due to like easy implementation on Linux, and once they are found successful, they get ported to other platforms. So we are constantly scaling on like other platforms like Windows, Android, and Mac. Lastly, I want to talk about our popular vulnerability rewards program. So I don't know, there is Tim Willis sitting in the crowd. He's our awesome VRP manager. If you really want to make some money, talk to him. So the Chrome Vulnerability Reward Program, it started in 2010. And we have paid at least like $1.6 million till date. This is just the Chrome VRP. In the Google-wide VRP, which spans across all the Google apps, that we have paid like around $4 million. It's a lot of money, so find bugs. Another successful program we had last year was we invited some of our top reporters to submit their fuzzer to run on our fuzzing infrastructure. So everyone really liked that idea because they don't have to do their fuzzing on just like one or two machines and be worried about all the hassles, waste time in test case minimization. Instead, they get the same fuzzing scale as us. And what we benefit out of it is we get all these reports like in the format we need ASAP and deliver like a fix and patch to our users quick. So it's like a win-win situation for us. And we have at least found like 100 bugs from the fuzzer contribution program, and we hope to make it public pretty soon too. Another thing we did last year was, actually Tim did a blog post. I wonder if you guys noticed that. We upgraded or we bumped up the baseline rewards for all of our security severities. And we paid even more money if the reporter provided like more explanation on the bug exploitability or patch suggestions, which really helps to prioritize our fixing as well. Okay, so the next goal. Next goal is on getting fully reproducible and minimized test cases. Yeah, so this goal is about actually making your developers really happy. So I don't know, if you hand like 100 kilobyte test case to your developer and they waste like a day hand minimizing them, they will really hate you. So instead now, we give them Clusterfuzz for minimizing both internally found and externally reported security vulnerabilities. And this is based on like a multi-threaded minimizer that is based on delta debugging. What it does is it generates a set of hypotheses that certain groups of tokens are not required for a crash. And if that succeeds, we remove those tokens. Otherwise, we break them up into smaller groups. We have custom minimizers for different formats. So things like for pure JavaScript, it's best to tokenize by like semicolons, by curly braces, and so on. Other thing we do is we do resource minimization. The reason being we have tests from all over the web. So it's not just like our test repository, but like things like IE tests, Mozilla tests, W3C tests. And we cannot really expect a developer to have all these test suites on his local machine. So instead we have this magical switch which captures both the remote and local and remote file loads, and that helps us to archive the dependencies pretty easily. Again, we go one step beyond that by making the developer's life easier with better stack traces. So every of these memory debugging tools I talked about before has a fast configuration, default fast configuration. But if you look at their flags documentation correctly, you can rerun them in a slow mode with more flags enabled that gives you better stack traces. Example being this case where if you increase the red zone size, you will really see that this heap use after free is actually a heap buffer overflow. Finally, so we have found a bug. We have minimized it. Now, time to get it fixed ASAP and release a patch to our users. The way we do that is by archiving each and every build across all of these memory debugging tools for the last 5 years. We make sure that these builds are good, that they don't crash on startup, and they have run a basic test suite so that we get the regression ranges and fixed ranges clear and correct. We do some optimizations too. Like when you're testing with thousands of these bots, many of the new bugs that you find are actually regressions. So if you just look behind like 3 to 5 bad builds, 3 to 5 builds, you will find that it probably regressed there. And if that doesn't work, we just go to a binary bisect. We do even more stuff, like even if you have a regression range, we help you to find what is a culprit CL, because things get really complicated with refactorings and regression, like large code refactorings, and if your regression range itself is pretty big. There is this project you can read about more. It's a Findit project. And we really found that for at least 85% of the bugs, it could give the culprit CL in the first result pretty easily. The way it works is pretty basic. Like it puts all like bucketizes stack frames into a set of components and crash lines, finds out which CLs change those crash lines, and done some more intelligent stuff. So things like, let's say if you are crashing inside a if block, but the actual trigger was somebody added a condition to this if statement. So it looks around the lines and makes decisions. And if it doesn't work, it will still show you a git blame info for you to assign an owner. So that's about it. Do we have 1 minute for a demo? OK. I need to change the resolutions. How do I change? How do I do that? OK. Switch. Oh, OK. Yeah. Let's see. OK. Yeah, that should be better. Sorry about that. So this is the main Clusterfuzz UI. So this page just shows us all the crashes. So instead of odoing Chrome, I'm just showing you a crash in a test proxy, which is like a test runner. And as you can see, it gives a good summary of what is like the test case looks like, where it regressed and stuff. You can click on a test case link to see more details. So this is what the test case report looks like. It will show you all the crash parameters, which I talked about before, whether this test case is reproducible, whether it's security or not, where it crashed, what was the regression range. And it will give you both the minimized and unminimized test cases. It will give you the suspected CL too, like who regressed it and why that was the case. So if your developer comes back and say, no, I didn't do it, you have some like explanation for that. And it shows you the stack traces in detail. Like you can even click on that, and that will give you a code link. So there is a pretty easy way to file the bug. So this is an old bug, which is now fixed. So as you can see, this was filed on the 6th of November. We had the culprit CL information. So it was pretty easy. I was a security sheriff that week with my cap on. I assigned it to the owner, and the guy just fixed it in a day. And then Clusterfuzz did the automatic validation for this too, verification. And there is another thing it does is there is a sheriff bot which tries to see which releases it impacts, and so it adds like the merge labels and stuff too. So everything is mostly automatic, like other than just assigning the owner, which we plan to automate too pretty soon. Other things are like this code coverage tag. So this shows for different components what sort of coverage we are getting. So we are constantly writing like new fuzzers or improving existing ones to cover more items. So to give you an example, like there was this libpng stuff, and we weren't seeing any of the 32-bit like code covered. So we knew we forgot to enable the fuzzer on that job type. And finally, there is this tab where you can upload a fuzzer, easily see what kind of test cases it generates, and so on. So that's about it. Thank you, everyone. Sorry, I ran a little bit for time. And all of the memory debugging tools I talked about are actually open source. And the Clusterfuzz code itself, we are planning to open source in the next month or two. And do have a lookout for the Chrome blog post on that. And thank you, everyone.